Chapter 7, Resistive Circuits. Resistive elements' basic behavior are very similar to those of capacitors. Because of this, I will rely on what we did in series and parallel capacitors to resistors. If you find yourself not remembering or understanding, I suggest going back to lectures 5.6 through 5.8 and rewatching those lectures. I will only give a brief review applied to resistors here. So I will only give a brief review applied to resistors following the series and parallel capacitors. So an outline on resistive circuits for right now should be where we do the following thing. First thing we should look at is that we should understand what do we mean by series and parallel basics. Resistive basics. And then we want to come in and we want to compare a series versus a parallel circuit. And then we'll try to put all of this together and we'll look at a challenging conceptual example before we jump into the actual calculations. I will follow up after all of this with getting into Kirchhoff's laws, which is a very different animal. So when I think about series and parallel resistive basics, we need to go back to the geometry. From the geometry, we talk about what does it mean to add things in series, which means its length increase. What does it mean to add things in parallel, which means its area increase. And then we're applying this to resistive elements. So here we go. So then our first lecture here, our focus here is then going to be on series and parallel resistive basics. So as if I already said here, the capacitance dictates the characteristic details of the capacitor. Where it's the product of dielectric material and geometry. However, macroscopic circuits only care about geometry. And for this reason, capacitance, which is equal to the area, proportional to the area, plus the plate separation, directs how capacitors are added in series and parallel. So now we want to do that with resistance. So resistance plays the same role as capacitance. In macroscopic circuits, we see that resistance is equal to the resistive material times the geometry of the resistor, which then is proportional to the geometry, which said that that's what dominates. And this is then going to be the length of the resistor divided by its area. So that's what we have to follow. And note, this is just the opposite of capacitors, because it's the opposite of capacitors, which is area over plate separation. How you add things in series and parallel are suddenly reversed. So just like we said about capacitors here, this geometry of resistance directs how resistors are added in series or parallel. So here we go. So the first thing we want to look at is the geometry of series and parallel resistors. So when we do this, I said that it's going to be the opposite of capacitors. So we're then going to find here is that so the geometry, and here's just a slight review here, the geometry of adding elements goes something like this. So if we add them in series, it increases length. If we add them in parallel, it increases area. Exactly the same thing with capacitive elements. Now, we apply this to resistive elements. So the first one that we'll look at is we'll look at series. So this is deep into pictures here, right? This is the physics of pictures. So the first thing here that we want to do is we're going to be adding resistors in series. So we know it has to add length. So we know that series increases length. So our pictures must show this. So what we have to do here is that we have to define a, so by the way, before I forget here, I'm going to use the resistor model as before. Okay, so here we go. So we need a reference restrictor. And it's this restrictor that we modeled this as a resistor. So if I have a reference restrictor, then this is what I'm seeing. I'm seeing that I have this guy right here. And then what it's going to do here is it's going to then restrict the pipe. So when I'm seeing this, this represents the wire in gray. The yellow represents the resistor or the restrictor. And what we find here is that this resistor should be proportional to length, where this guy here represents the length of that guy. Now, if I start adding these guys in series, what does this picture mean? Well, it starts to look at something like this here. I have to draw them in series, so then I'm going to have a restrictor. You could see that I'm adding 3 of them together. And so if I look at this picture, then I'm going to draw my wires. I'm going to draw in my resistors. And as you see here is that this is going to be R1, R2, R3. And of course, this is proportional to the length. Now note that these guys can have different lengths. So I could come in here and I could go 1, 2, 3. So the equivalent of this is that I could now replace this with one equivalent one. And if I do that, then I'm going to have to pick something like this here. So I'm going to have a wide, and then this guy has to be 3 times the length. So if I look at this, each of these restrictors can be drawn equivalently as one single one. And so when I look at this, this is what we call series. And you could see here is that the series says that they're proportional to the lengths of these guys. So then what we say here is that by adding them in series, it increases the effective length of this resistor here. So now I can do the exact same thing with real resistors. They behave that length. So when I come in and I look at this, we could now say that we're going to add resistors in series. So then again, I start off with a single resistor, which is this guy right here, and this will be our reference. And now I got to compare it to 3 of them. So if I do that, then I'm going to go 1, 2, 3, and then of course this will be R1, R2, R3. And if we compare them, we're really comparing one of these guys to 3 of them. So the equivalent model then says that I should have a resistor then that's 3 times the length of 1. And then we say that this is our series because it's directly proportional to the length. So then we could then come in and we could just say this is, this is then going to be R1 plus R2 plus R3, where we could see here is that if I look at our series, the length of our series is bigger than any of these guys, right? It's bigger than any of these. So this is R1. So our series has to be bigger than R1 or R2 or R3. So just to stress this again, our series is larger than any one resistor, right? That's what we mean by our series right there. I actually want to box this up here. So I'm going to move this down a little bit. Right here, I'm going to put a box across this because this is the important piece. So I'm going to come in here and I'm going to say, this is what we were after. If we add these guys in series, this is the consequence that we see here. It's the geometry of the resistance that dictates how we add them. Okay. Again, because of the geometry, right? Because of the geometry, of series resistors divide the voltages while keeping the same current through each resistor. So let's look at the details. So let's talk about the voltages are divided. So if I look at this thing, I'm going to say that voltages are divided. And so picture-wise, we need to draw let's say we draw 3 resistors. I don't have to draw 3 resistors. I could do 2, I could do 4. It does not matter. So when I'm looking at this, I'm going to come in here and I'm going to draw this right here. So I'm going to go 1, 2, 3. And so when I'm looking at this, I imagine that I have a source. And I have resistor 1, 2, and 3 here. And what I see is that the source here is now going to put out some voltage, which we're going to call the source voltage. Now, if I look at this thing, here's what I'm finding. If this is ground, then that means that the whole line across here has to be 0. If this is the voltage source up here, then that whole line here has to be the voltage source. So when I look at that voltage source, we can see that there's a height. And I'm going to say that right here, this is the total potential height. And we're going to say that this is V source. But now what we're going to find is that you can see here that these voltages, because of this, we can split these resistors in any possible way that we like. So what do we say? We say that if this guy has a voltage of delta V1, then that means here that that height has to be V1. If I cause this guy to be V2, then this height has to be delta V2. And if I just keep repeating this process, then all 3 of these heights must equal the voltage source. In other words, the voltage source height has to equal all 3 of these guys right here. And so this plus this plus this gives me the total height. There's an actual name for this equation. It's a little bit more detailed than this, but it's known as Kirchhoff's. Oops, I spelled that incorrectly. Kirchhoff's voltage law. And it's a very important law. So a lot of the times I call this KVL. That just says that the total height has to be the sum of the individual heights. That's how voltages are divided. Now, what about series? So I'm going to take this and bring this with me. So what we say here is that currents are not divided. They're the same. So we then say series currents are all the same. In other words, they're not divided. There's lots of ways to show how this is the case here, but it's really comes down to something called charge conservation. So what it says here is that charge cannot be created or destroyed. If you were, let's say, destroying it, then the universe, let's say you destroy negative charges, then the universe is going to be more positive. If you destroyed positive charges, it would be more negative. And that's not what's observed. In any interaction, since series has only one possible path, there can only be one current flowing through the circuit. And so if I use that circuit that we just created here, and then I'll just modify it, but you could imagine that I have something like this, right? I don't need my nodes anymore. And I definitely don't need the voltages because we're not interested in voltages. We're only interested in currents here. So by modifying this, what you'll see here is that I'm going to go follow the currents. So if I follow the currents, then what's happening here is that I have a source current. So the source current comes out of the battery. The source current comes back into the battery. So that means here that source current has to flow through resistor 1. There's no division here. There's no creation or destruction of charge. Then it flows through 2, and then it flows to 3. And then it comes right back as the source current. And these guys are all the same. So what we're saying here is this, that the current of the source, in this case, is going to be 1 plus 2 plus 3. And this is another famous law. Up here, we just talked about Kirchhoff's voltage law. This turns out to be Kirchhoff's current law, which we call KCL from time to time here. So that's all that we have for series here. So now we're left with parallel. So now the second thing that we want to do is we want to talk about adding resistors in parallel. So we've talked about this already, adding any element in parallel causes an area increase. That's no difference here. So now we're going to go back to our resistive model here, and we're going to have a reference again, a reference restrictor. So when I look at this reference restrictor, it's going to look something like this. It's going to have, just like we talked about before, and so in this situation, we're looking at area. The resistor now is proportional to the area. And of course, this is the area right here. So now I got to draw 3 in parallel. So when I look at this, here's what I'm seeing. Okay, I think this is going to be a tricky draw. So I'm going to start off wide. I'm going to adjust things so Then I'm going to come over here. Then I'm going to have this resistor here. No, I think that's going to be too wide. So I want one that's going to be effectively 3 times the width. Okay, so that's an approximation right there. So now I'm going to restrict it. And then I got to unrestrict it and bring it all back together. So now I have my circuit. So when I look at this thing, once again, here's my wire. My wire has to be thicker than the restrictor. So now if I put in my restrictors, we can see here that this will be R1 proportional to 1 over the area of 1. R2 proportional to 1 over the area of 2. R3 proportional to 1 over the area of 3. So why does this reduce resistance? Because I have a bigger overall area. So when I look at this guy, I'm then going to come in, and this guy should be 3 times as wide. So if it's 3 times as wide, then that means charge is going to flow through it easier. It's easier going through a smaller restriction than it is a bigger restriction. That's what we now call R parallel, but R parallel adds the inverse of these guys, which will then be proportional to 1 over A1 plus 1 over A2 plus 1 over A3. So if I was to move this over a little bit, you're seeing here is that what I have done in this situation, we have increased the effective area, therefore reducing resistance overall. So now if we go and we try to do this with resistors in parallel, we then can say that resistors in parallel follow this too. So I have so let me draw the 3 first. So I'm going to say that I'm going to come here. Then I'm going to have one resistor. Then I'm going to have my other. And then these guys are all going to connect. So if I compare this resistor to this resistor, this is what we call R1. And now we're going to compare this to R1, R2, R3. even though we don't see that we're making the area larger, like we did with this restrictor image, we can say that if I look at this guy, that only has this effective area. But these guys have 3 effective areas that we're adding together. We can't visually see that, but we could just come in here and just say, if we do add them in parallel, then 1 over parallel is equivalent to adding the inverses. And this equivalence is the equivalent of increasing area. Where in this situation, we then say that R parallel is always going to be smaller than R1, R2, R3. Now note, you can't see that looking at the resistive circuit, but you can see this here. The fact that this is a thinner one in R1, that means that the resistance R1, that forms a bigger restrictor than R parallel, so therefore it has higher resistance. That's what this relationship, R parallel, being less than all of them. So in other words, R parallel is smaller than any one resistor. So we now have this. So now let's go back to the geometry of this. And we then say the following thing. Because of the geometry of parallel, resistors divide current while keeping the voltages the same. So let's look at this. So if I have a parallel circuit, so if I'm looking at parallel currents, we have to say that parallel currents are divided just by the geometry. So let's draw this in. So in a parallel circuit, current can take multiple paths. So let's look at this. So I have 3 resistors. And I'll call this R1, R2, R3. Now I'm going to connect this to a source here. So because I've connected to a source here, I could now start to follow the currents here. So I know that I'm going to have current coming out of the source. And then I have current coming here. And now I have my junction right here. I have my node. So what happens? The current has to split. One of the currents is going to the left. One of them is going straight down. The other is going to the right. And then what happens? They come in here and they reconnect again. And as they reconnect again, then at this junction again, since we cannot create or destroy current, then I have my source current that's now coming right back into the battery. It has to divide the currents here. So if I do the same thing for voltages, by the way, I should have said this already. We talked about Kirchhoff's current law, but I could clearly say here in this situation that I source has to be the same as I1, I2 plus I3. And this is Kirchhoff's current law. So if I look at voltages, we then say that parallel voltages are the same. So since, and the way I'll do this here is that I will draw this slightly different. And one of the things that we got to remember here is that if elements have two nodes slash equipotentials, connecting them, they are in parallel. That means here that we have two potentials and one voltage across all parallel elements. So if I draw this out, we could then say it's something like this. So if I have my source here, now let's go put in my resistors. These guys are also in parallel and they're equal to our other circuit that we just drew above. So what that means here is it means this, that if this is resistor 1, resistor 2, and resistor 3, you're seeing here that the upper node, the red node, has to be the source potential. But only potential differences make a difference. So then the bottom here, we can define as the ground. And you could see here that there's only two nodes. So then if I define this as voltage 1, voltage 2, and voltage 3, then it says that they must all have the same voltages. Therefore, parallel elements must have the same voltage.